Welcome back to the explainer. Now, we all know that a tiny pinch of a trace element, something like chromium, can magically turn a totally colorless crystal into a vibrant red ruby. But today, we're actually moving past gemstone chemistry. We're going to uncover the invisible physics of light and crystal structure. Basically, we're going underneath color itself to understand why these stones truly captivate us. So, to kick things off, let's pose a really fascinating question that trace elements alone just can't answer. Why does a perfectly cut diamond shoot out rainbow fire all across a room, while an identically cut emerald simply doesn't? I mean, imagine them, cut to the exact same specifications, sitting side by side. That emerald is never going to throw those spectral flashes. And the answer? Well, it's not in the gem's color. It's actually in something far stranger. It's in the literal geometric layout of its atoms. Here's our roadmap for solving this little mystery today. We'll start with the 7 crystal systems, then we'll hit refractive index, birefringence, pleochroism, and dispersion before bringing the whole shebang together at the end. Let's jump into section 1, the 7 crystal systems. The very moment a crystal begins forming deep down in the earth, its atoms get locked into a permanent, 3-dimensional geometric pattern. You can kind of think of it like a city's street grid, but for atoms, right? Some cities are laid out in perfect, highly symmetrical squares, while others sort of sprawl out at odd, intersecting angles. Well, this atomic grid never changes, and it dictates exactly how light is allowed to travel through the stone. Mineralogists actually recognize just 7 of these repeating crystal systems in all of nature, and every single gemstone belongs to one of these. Diamond, for instance, is perfectly symmetrical. It grows in the cubic system. Meanwhile, corundum, which is the family for ruby and sapphire, well, that utilizes the trigonal system, a completely different geometry. And this crystal system is absolutely crucial. It is the master key governing everything we're about to cover. Moving right along to section 2, refractive index. If you've ever been totally mesmerized by a gemstone tilting under a jeweler's light, well, this right here is why. The refractive index, or Ri, is essentially a stone's sparkle number. When light travels from the air into a denser material like a gem, it naturally slows down and it bends. So the refractive index is really just a numerical measurement of exactly how dramatically the material forces that light to hit the brakes and bend. And comparing different materials shows us exactly why a diamond looks so much livelier than, say, a piece of glass. Look at water. It has a pretty low Ri of 1.33. Glass sits right around 1.5. But look at diamond way up at the top. Because its Ri is just so exceptionally high, it forces light to bend drastically and literally ricochet around the inside of the stone before finally blasting back out to your eye. So it's not just a clever cut doing the work, it's hardcore physics. That extraordinary number right there, 2.42, represents diamond's incredibly high refractive index. It's literally one of the highest of any naturally occurring gem material on Earth. And again, that is baked directly into the mineral's geometric physics from the exact moment it formed. Let's dive into section 3, birefringence. This is where things get a little wild. Also known as double refraction, birefringence happens when light hits certain crystal structures and actually gets divided into 2 completely distinct paths. That means a single ray of light enters the stone, but 2 separate rays of light travel through it, and they're each moving at slightly different speeds and bending by different amounts. Pretty crazy, right? This beautifully contrasts the difference between our 2 atomic grids. Highly symmetrical cubic crystals, like diamond, are optically singly refractive, meaning light just passes through in one single path. But non-cubic crystals, like our trigonal corundum, are birefractant. And this is actually super practical for gemologists. If you look through a birefractant gem under magnification, right along the correct axis, you can actually see a visual doubling of the back facets. You literally see double. It's a fantastic real-world diagnostic test they use all the time in the field. Which brings us to section 4, Pleochroism. Now, Pleochroism sounds like a magic trick, but I promise you, it's pure crystallography at work. It means the gem's crystal structure actively absorbs different wavelengths of light depending entirely on the angle the light travels through the stone. In plain English, you look at the gem from the top, it's one color. You look at it from the side, and boom, it's a completely different color. The absolute textbook example of this is tanzanite. I mean, this stone can display blue, violet, or even a brownish-red, depending entirely on your viewing angle. And no, this isn't some trick of the room lighting. It's the crystal lattice physically interacting with the light.
Because of this, master lapidaries literally have to sweat over the rough crystal, orienting it incredibly precisely before they even think about making their cuts. If they get the angle wrong, the gem looks kind of muddy. But get it right, and they showcase the absolute best, most desirable color face-up.
All right, Section 5, Dispersion. And this right here is the answer to that big diamond mystery we posed at the very beginning of this explainer.
So the crucial piece of the puzzle is understanding this exact property. Dispersion measures a material's ability to act like a tiny prism and separate white light into a rainbow. See, while refractive index gives the gem its overall brightness or brilliance, dispersion is responsible for this dazzling property that gemologists simply refer to as fire. Because diamond has such an unusually high dispersion value for a naturally occurring gem, its calculated facet angles don't just return bright white light to your eye. They act as microscopic prisms that throw out those famous rainbow flashes all across the room. And emerald, it just doesn't have the same dispersion power within its atomic grid. So this right here is the actual physics behind the sparkle.
Finally, Section 6, Bringing it together.
So how do we synthesize all this? Well, a gemstone's identity is truly a tale of two systems. On one side, we have chemistry. Trace elements like chromium give a gem its beautiful color. But on the other side, we have crystallography. The underlying crystal system is what dictates the spectacular light show. Chemistry provides the color, sure, but that atomic grid provides the brilliance, the double refraction, the pleochroic shifts, and of course, that fiery dispersion.
So, what should you take away from all this? Well, the next time you walk past a jewelry store window, try not to just look at the colors. Ask yourself, what invisible atomic grid is bending, splitting, and throwing that light back at my eye? Are you seeing the cubic fire of a diamond, or maybe the trigonal doubling of a sapphire? Understanding this hidden physics completely changes how you look at the world around you. Grab 2 gems we talked about today and compare them for yourself. Thanks for joining me for this deep dive into gemstone crystal optics. Keep exploring, stay curious, and I'll catch you in the next explainer.